Good morning, my dear students. In this session, we are going to start a new chapter. The name of the chapter is Electromagnetic Induction. In short form, it is written as EMI. Look at here, my dear students. We had already discussed a topic called magnetic effects of electric current. Magnetic effects of electric current. In magnetic effect of electric current, what we have discussed? From electricity, there is a production of a magnetism, isn't it? This is the phenomenon was discovered by a scientist called Ørsted. I hope you could recollect and remember the previous things. Now, this electromagnetic induction is exactly the reverse process of this. The reverse process of this means, how can the phenomenon of magnetism can produce electricity? How can a phenomenon of magnetism can produce an electricity? It's so simple, right? So from the magnetism, how the electricity can be produced? This is what the phenomenon was first developed and discovered by the name of the scientist called Faraday. So initially, the scientists have thought that there is only one-way process from electricity to magnetism. A general question comes into the mind of the scientists as well as us. The opposite is true or not? The reverse is possible or not? That's a general question. With the same general question, the scientists have decided to work on, and they have found finally there is a possibility of production of electric current from the magnetism. Why and how? That's what we will discuss. And that's the name of the chapter called Electromagnetic Induction. In most of the concepts related to this chapter will be associated, look at here, will be associated with the topic called magnetic flux change. What is this? A magnetic flux change. Look at here. And even this electromagnetic induction is also the phenomenon which is associated with the magnetic flux change. Let us understand the magnetic flux change. So then we will move to the topics called Faraday's experiments. First, about magnetic flux we will discuss. About magnetic flux or electric flux you might have discussed in the last previous classes or the chapters. The magnetic flux is denoted with the symbol phi. And this is the magnetic flux is equal to B bar dot A bar. And this is magnetic flux is a scalar quantity. Carefully see, it is a scalar quantity. And this can be written as BA cos theta. Alright. Imagine the theta value is 0 degrees. You can say the magnetic flux is B into A. Cos 0 is 1. There is a maximum flux here. So if theta value is 90 degrees, so you can say phi is equal to B into A into cos 90 is 0 and 0 flux. If theta value is 180 degrees, so you get the magnetic flux is equal to B into A into cos 180, which is minus 1, it is a minus BA. I hope you could recollect the SI unit of a magnetic field or field induction is Tesla or Weber per meter square. This is what we have learned already. How Weber per meter square you will understand now, and look at here. So the magnetic flux is equal to BA. Let's take the condition of theta is 0 degrees. And what is theta here? The theta is angle between B and A. I'll explain with the NEET diagrams also. So magnetic flux is equal to BA, and here B is equal to phi by A, and this is Weber per meter square. And carefully see, magnetic flux SI unit is Weber, right? So SI unit of a magnetic flux is Weber, denoted with the symbol WB. And at the same time, CGS unit also, I'll write here, CGS unit is a Maxwell. What is that? A Maxwell. It's the name of the scientist. And there's a relation between these two here. 1 Weber is equal to 10 raised to 8 Maxwell. Right? Magnetic flux linked with a coil. A magnetic flux linked with a coil. Because most of the topics related to this chapter linked with this topic called, it's a small topic called magnetic flux linked with a coil. Imagine there is a coil here, a rectangular coil for example. You know its area vector will be in this way. So imagine that's A bar. This is B bar. The angle between them is theta, and the magnetic flux linked here BA cos theta. This we know. Here if this is the rectangular coil and the area vector is this one, now the magnetic field lines are moving in this way. These are the magnetic field lines. Carefully see. What is the angle between them here? It's 90 degrees. Then in this case, magnetic flux BA cos 90, so which is 0. There is no flux linked with the coil. Understand? Clear? Now, a rectangular coil is here, area vector is here, and the magnetic field lines are also passing along the area vector direction. In this case, theta is 0 degree, so B is equal to, phi is equal to BA cos 0 is 1, it's BA, maximum flux linked with the coil is in this case. When there are n number of turns for a coil, when there are n number of turns, I can say magnetic flux linked with the coil will be NBA cos theta. Remember my dear students, flux change should take place means there must be a change in number of turns, or there may be a change in magnetic field line strength, there may be a change in orientation, that means theta, or area vector of the rectangular coil need to be changed. So magnetic flux change need to take place when it is depending on all these physical quantities, then the magnetic flux change. Understand? Clear? So magnetic flux change is the most important point, most important topic in this chapter called electromagnetic induction. Alright. Now, let's move on to Faraday's experiments. Before moving to that, let us solve a simple basic numerical of a magnetic flux. Look at here. A uniform magnetic field exists in a space where a B bar is B1 I cap plus B2 J cap minus B3 K cap. Find the magnetic flux through an area S bar if the area S bar is in S bar is in YZ plane. Let's consider. Our aim is to find what? Magnetic flux. Formula for the magnetic flux, as they have given in the vector form, I am writing in the vector form, B bar dot A bar. Let's consider this question. YZ plane. Imagine this is what the rectangular coil I have. This is your Y axis, carefully see. This is your Z axis. Simple. Now my rectangular coil is in YZ plane. Understand? YZ plane. Its area vector will be perpendicular to the plane. So this is the area vector. So if it is Y, if it is Z, so definitely perpendicular to the plane it will be X. So that means it is I cap direction. My area is in I cap direction. Okay. So I am writing here, this is instead of A bar, let me write S bar because they are given in terms of S. Now, this S bar is in which direction? S into I cap. Alright. Area vector is along I cap direction. Its magnitude is I. You know the unit vector form. That's all. Now, simple. Phi is equal to B bar. B1 I cap plus B2 J cap minus B3 K cap dot S bar. S I cap. Phi is equal to B1 I cap dot S I cap. Understand? As cos 0 is 1, I cap dot I cap is 1. So I can write B1 into S. So that's it. This is the magnetic flux associated with the coil, with the rectangular coil, when the coil is kept in YZ plane. It's so simple. If the coil is in YZ plane, its unit vector, its area vector will be in X plane, sorry, in X direction. If the coil is kept in XY plane, your area vector of the plane will be perpendicular to this, means along Z axis. So this is perpendicular to this plane, the area vector will be, and that indicates the area vector will be along Y axis. So now you solve these two as class work and send me now. Just pause the video, send these things to me now. Now, example, another example, see. B is given, theta is given, A is given. Directly they're asking you to solve magnetic flux. So I have not drawn the diagram, so let me draw the diagram for you. This is your area vector, and this is the how the magnetic field lines they have represented, magnetic field lines. But this is the angle, it's given as 53 degrees. For that cos 53 triangle you should know. So this is 37, 3, 4, 5, 37 degrees triangle, and this is 53 degrees. Now let's move on. BA cos theta. Phi is equal to B 42 into 10 raised to minus 6 into A 2.5 into cos 53. Cos 53, this is 53, right? For 53 angle, this is opposite side, this is adjacent side, and this is hypotenuse. cos 53 will be adjacent by hypotenuse. So that I can write cos 53 is 3 by 5. 3 by 5, my dear children. That's it. 2.52s. Right? So phi value will be 42 into 10 raised to minus 6 into 3 divided by 2. So this is 221. So 21 into 3. 2 3 6, 1 into 3. It's 63. 10 raised to minus 6, I can also write it as mu, like how the given value, right? Mu. And the magnetic flux, SI unit of magnetic flux, I am writing it as Weber. So 63 mu Weber will be that. Is it clear? Is it simple? So these are very simple concepts. When you are confident and focused about the magnetism and magnetic effects of electric current, so these things will be very easy for you. Now, Faraday's experiments we are going to do. Faraday's experiments, a theoretical analysis we are going to do on Faraday's experiment, and it's so interesting and important experiment, which gives you the base for the topic name and the chapter name called Electromagnetic Induction. Right? Let's see. Simple. There is a coil. It's a coil. And for this coil, a galvanometer is kept. Why the galvanometer will be kept? So this is galvanometer. Why the galvanometer will be kept? Galvanometer will be kept to check the presence of the current in the circuit. In the circuit, whether the electricity is produced or not, you can check by using galvanometer. So there is a coil. So actually the coil is placed like this, not like this. Coil is placed like this, and there is a magnet, a bar magnet, whose north pole is placed here and the south pole is located here. It's placed here like this. There is a bar magnet. So this is the point. Imagine the black color is representing the north pole of the magnet. See here, like this. So magnet is moving towards the coil. When the magnet is moving towards the coil, there is an observation found in the galvanometer. Galvanometer is deflecting. So galvanometer is deflecting. That indicates there is a current passing through the coil. Yes or no? So without the current passing through the coil, the galvanometer will never deflect, but it is deflecting. So how the current is flowing? In this way. Right? Just a normal direction I have mentioned. Why the current only moving in that direction? That comes later. About the direction we will discuss later. First, there is a presence of the current in the coil is found by Faraday. Okay, when the magnet is moving towards this way. When the magnet is moving away, the deflection is reversed. If you imagine that it is anti-clockwise, when the magnet is moving away from the coil, so the deflection is reversed. Right? So I am writing here. So the deflection is reversed. Simple. When the magnet is kept at rest, no current is detected. Alright? When magnet is simply kept at rest, see, initially magnet is moving towards the coil. There is a current produced in this coil. Magnet is moving away from the coil. There is a current produced in this, but the direction of the current passing through the coil is changed. Now, the magnet is simply kept at rest. Anyway, it is at rest. Anyway, the coil is at rest. When magnet and coil both are at rest, no current. Now the coil starts moving. Understand? Coil starts moving. Coil is started moving towards the magnet which is at rest. There is a current. Both are moving. Both coil and the magnet moving towards it, away from it, whatever it may be. So there is a current production. Now, both the coil and magnets are moving with the same speed. with the same speed. Imagine this is the coil and this is the magnet moving with the same speed. Fine. What is the relative speed here? When two trains are moving in the same direction with the same speed, what is the relative speed? Relative speed is how much? 0. Same way, the relative motion is 0 when both the coils are moving with the same speed. Understand? When one coil and the magnet are moving with the same speed, so there is no relative motion present over there. Understand? There is no relative motion present over there. No relative motion. In which cases? In this case, no relative motion. When both magnet and the coil both are at rest, there is no relative motion. When there is no relative motion, no current is produced. That means relative motion is must. Between the coil and a magnet, relative motion is must for the production of the current. Okay, why the current is produced, I will tell you now. Listen to me. A very important and interesting topic comes here. And the current, whatever is produced here, so that is called induced current. What is it called? Induced current. Because that is not the current which comes directly from a battery. There is no battery here. But still current is produced. See, induced current. See, current need to be produced, there must be a battery which must have some EMF. Yes or no? But without the battery, without the EMF, there is a current. So that's called induced current. Come back to this coil. In which current is passing? That case, let's consider the current which is passing in this. Imagine the current is passing here, so that means there is an induced EMF also develops. Induced EMF also develops. Without an EMF, no current will be produced. EMF of a battery, original EMF of a battery, original current. Induced EMF, induced current. So there are some imaginary positive and negative terminals will be developed here. So that's called induced EMF. Imaginary. Why I am telling you imaginary is, as long as this relative motion exists between the coil and the magnet, so there is an induced current. When there is no relative motion exists between coil and the magnet, definitely there is no induced current. Induced, induction, what is meant by that? As long as some phenomenon is taken place, there is a production here. When that phenomenon is stopped, nothing. You got it? Clear? So that is called electromagnetic induction. Electromagnetic induction is, I am writing here, electromagnetic induction is the phenomenon. So simple. Electromagnetic induction is the phenomenon in which, look at here carefully, in which induced current and induced EMF is produced, induced current and induced EMF is produced due to the magnetic flux change. What is that? Due to the magnetic flux change. So this is the electromagnetic induction definition, my dear students. If you carefully observe the situation, when a magnet is kept here, see, it will have its magnetic field lines around it. Carefully see. It will have its magnetic field lines around it. When it is just kept here, when it is just kept here, carefully see, when it is just kept here, there are some magnetic field lines passing through the coil. Yes or no? There are some magnetic field lines passing through the coil. There is some flux associated with the coil. When you are moving the magnet towards the coil, more number of field lines will be passing through the coil. That means the flux change is happened. that may be more field lines passing through the coil or less field lines passing through the coil. The flux changes happened, yes or no? Yes, there is a flux change. Understand? So when the magnet is moved towards the coil, the flux change took place. When the magnet is moving away from the coil, the number of field lines passing through the coil decreased, whatever it may be, there is a flux change. Clear? In that way. So that, like this, you may move the magnet by keeping the coil rest. You may keep magnet at rest and move the coil. You may move both of them with different speeds in the same direction or in the opposite direction, whatever it may be. As long as there is a magnetic flux change, there is a production of induced current and induced EMF, and that's called electromagnetic induction. This is one of the simple experiments done by Faraday. Look at here, the another experiment. See, there are so many experiments. Let me discuss one more with you. That's it. Only one more. So there is a coil here. Same galvanometer is kept here. Here another coil is present just beside. So there is another one coil here. So there is another coil is kept here. Another coil is kept. But interestingly, in this coil, so there is an electric current passing through it. Right? First case, direct current means direction of the current is same. And the magnitude is also same. See, a constant battery is supplied here. So current is flowing. This is the actual current. When there is a current passing through this coil, definitely surroundings of this magnetic field will be produced. Yes or no? So some constant current will produce constant magnetic field. So that constant magnetic field lines will be passing through this. There is no flux change. Yes or no? Just some magnetic field lines are passing through. Flux is different, flux change is different, remember. There is a constant magnetic field lines passing through this. Galvanometer will not show any deflection. Now, when you keep on changing the battery or polarities, when you keep on changing the battery or polarities, what happens? The magnetic field produced here also will be changes, because direction of current is changing, direction of field lines will be changing, the field lines passing through this also will change. Suddenly more number of field lines pass through it. When you change the polarities, number will become less, and again it will become more in the opposite direction. There is a constant magnetic flux change linked with this coil, and that will produce induced current. That will produce what? Induced current. Okay. Now, when there is an alternating current is produced, alternating current is kept here. The source, alternating current source is kept here. Then the direction of current is automatically reversed for every half rotation. Then the constant flux linked with this coil. This is then another experiment. Alright? Clear? So, but one thing you should understand, if the current direction, actual current direction is clockwise and induced current direction will be anti-clockwise, just it will be opposite to that. Okay? Clear? So these are the Faraday's experiments, and this is the basic numericals. And now let's discuss the Faraday's laws of electromagnetic induction. What is electromagnetic induction? You understood just now. Now Faraday's laws of electromagnetic induction. So there are two important laws of Faraday based on electromagnetic induction that we'll discuss, and those are the things already we have discussed in these two slides. Same things. Let's discuss in a definition form. Faraday's laws of electromagnetic induction. Number one, whenever, this is an important question for your second PUC board exams, and the numericals we will be solving soon. Whenever the magnetic flux is linked with a coil changing, magnetic flux linked with the coil changes whenever it is happening, and an EMF is induced in the circuit. That's what I told, we discussed already. An induced EMF will be generated. The induced EMF exists as long as the change in flux continues. Alright? As long as there is a change in flux, there is a production of induced EMF. From the induced EMF, induced current. Induced EMF is nothing but the imaginary or the virtual polarities of a battery. Second, the induced EMF produced in the coil is equal to the negative rate of change of magnetic flux linked to it. The rate of change of magnetic flux is d phi by dt or d by dt of phi, because with respect to time there is a change in magnetic flux. Yes or no? Imagine there is a coil is kept here, magnet is kept here. With respect to the time, magnetic flux linked with this coil is changing. You can see here. Here flux change is small. Here the flux change is more and more. Understand? So that's why rate of change of magnetic flux is equal to induced EMF. Simple. The induced EMF produced in the coil is equal to the negative rate of change of magnetic flux. And forget about the negative symbol. The negative symbol comes according to the direction. According to a direction of induced current, right? So that we'll be finding in a coil the direction of the induced current we found by using Lenz's law. By using what? Lenz's law, right? By using Lenz's law. So that is the next topic. And before that, this is the relation is called Newman's relation. Newman's relation or the equation, Newman's equation, right? But the negative sign is according to the Lenz's law. No need to worry, and we'll be discussing in the next class, right? So come back to the Newman's equation. E is equal to minus d phi by dt, and we know it is minus d by dt of phi. Phi is NBA cos theta. Can I write like this? Magnetic flux is NBA cos theta only, right? So this is how we'll discuss the topic, and the numericals also can be asked in this way by giving a magnetic flux values like this. For example, if the magnetic flux is 2t square plus 3t, and the question is find the EMF induced. Find the EMF induced at a time 2 seconds. So simple. E is equal to minus d by dt of 2t square plus 3t. So this I can write it as minus keep it aside. D by dt of 2t square, it is 4t, plus d by dt of 3t, it is 3. Time is 2 seconds, substitute here. So E is equal to minus 4 into 2, it is 8 plus 3. How much it is? Minus, it is 11. So induced EMF, whatever maybe, it is EMF only. So minus 11 volt will be the answer. Minus 11 volt we have got, and you should not get confused with the negative sign. As we had already discussed, negative sign is in connection with the direction of induced current. So that's why the magnitude of the induced EMF will be 11 volt. Alright. All the very best for your offline 5 questions assignment. Thank you so much.